Hello everyone and welcome back to episode 3 of the Rocketry series. So, yes, what I'd like to do over this episode and maybe the next couple is we're going to kind of do a follow along, let's scratch build a rocket and build it. I'm going to basically hopefully give you the principles of how you can build a scratch built rocket and design a scratch built rocket, but you don't have to match exactly what I do. So don't worry about finding exact matches for the tubes and the components. I want to build something roughly this size. This is the first model rocket that I designed and scratch built. I love it dearly, but equally it's got a few things that I'd like to change. I don't like the way I did the motor mount. I don't like it sticking out of the end. Inside I've used a kind of stopping block, which means I can't use longer motors, which I now want to do. Yeah, but there's some things I do really like about this rocket. It's about as big a rocket as you can launch on the standard Estes launch rail. It's got plenty of room inside for any type of parachute or streamer thing that you'd want to deploy to slow you down as it comes back down. Loads of room inside it for that. I've built the top section is actually a payload section. So when this flies up and goes over and deploys its parachute, it doesn't blow the nose cone off. It actually blows apart here. So I've made a coupler, and yeah, that means that this upper payload section is empty, and it's designed so that it needs a little bit of weight in there. So it's perfect for if you want to fly maybe a DIY altimeter, or if you want to buy an altimeter and place it in there, or indeed like my kids love flying Lego figures and stuff like that. So it's a really versatile little rocket. So as such, I've found a tube that's roughly about the right size. This is not a special snazzy tube. This is quite a cheap, not great quality cardboard tube that's come out of some wrapping paper, as indeed was this one here. It's going to do the job fine. It's not too thick, which is kind of what you want. Sometimes you get, this is not a bad tube, you could build a rocket out of this. This came out of maybe some tinfoil or something, but you can see that it's a bit thicker, so it's a bit of a heavier kind of tube. You could certainly build a rocket out of something like that, but I'm going for this size, and I like that this is quite a lightweight tube. First thing you want to do is measure how much tube you've got lengthwise, get a tape measure on it so that you know how much you've kind of got, because ideally you want to make the booster section and the payload section out of the same tube so that all the diameters match. And then a good place to start is to identify all the diameters of this tube. So the internal diameter and the external diameter. And therefore you should be able to work out the wall thickness as well. To do this, you could just use a ruler. Be careful to try and get it on the widest part of the tube and work out what your internal diameter is and your external diameter is. That's going to be a little bit crude, but it'll work. What it means is later on when you build things to fit inside, you might have to have a few trial goes before sort of getting the exact kind of size that you need. And if you want to spend some money on some useful rocketry tools, or if indeed you have these for something else, some other project you've had them for, these are a brilliant rocketry tool called telescoping gauges. And what they do is these are spring loaded, and you can insert them into a tube with these compressed, and then you tighten up this base bit here, and it will hold them at the diameter. Then you can take them out of the tube and measure across. So I'm going to use these to work out the inside diameter of this tube. So gently squeeze those, get it in there. What a lot of people do actually is they put them in at an angle, half tighten them, and then force them up to take the full diameter and then fully tighten them. And then you take them out. So this across here should now match the inside diameter of this. Well, let's just check that my calipers are zeroed. Yep. So measuring across here, and again, if you want it to be really accurate, you might use a micrometer on this. What have we got there? 42.5 millimeters roughly. So there we go, so that's 42.5. Let's do a quick measure across here. That's looking at 44.8. So looking at maybe just over a millimeter for each wall. Now that one's looking at a millimeter. Yeah, a millimetre. Yeah, it's looking consistently about a millimetre wall thickness. So there we go. Once you've got those bits of data, useful as you've seen already, measure it at a few different points because these cheap cardboard tubes will fluctuate a little bit. Once you've got some data on your tube, let's move over to OpenRocket and put some of these dimensions in and start to build a rocket around the tube that we have. Okay, so we've moved into OpenRocket, having measured our tube, and the tube that I had about 70 centimetres length of tube, and so I had plenty to design a rocket similar to the one that I said I wanted to replicate in the first part. So I've just whipped up a quick OpenRocket. I'm not going to go through everything because that's in the previous video, but so just quickly, some of the key features are the upper payload section. I've gone for 15 centimetres of tube for that, and the lower booster section is 40 centimetres long. The nose cone is 10 centimetres long with a couple of centimetres shoulder. Again, I've set that currently as being made out of PVC to add a little bit of weight. What we'll do is probably for my nose cone, we'll 3D print it and then I'll weigh it and I'll override that. Don't worry if you haven't got access to a 3D printer. We'll talk about some ways that you could potentially make a nose cone. Although I do suggest try and get access to a 3D printer because it is a very nice way to make a nose cone. Similarly, this coupler here, which is the bit where the rocket separates, so it will be glued in and stuck in on this side into the upper the payload section, but it will be a kind of sliding fit on the lower section. Might actually need to be a little bit longer than that. I might tweak that. But I've made that with a wall thickness of what was it, 5 millimeters? Yeah, half a centimeter. The reason for that being is again that I'll probably 3D print it, and to get the strength in the 3D print, you're looking at about 5 millimeters if you're printing in PLA with some infill, etc. Other things that I've added. Oh yeah, I've added a. If you click on the top tube, you can add a mass component, which is this black outline I've added here. It comes up as unspecified. Of course, you can select that and change the name. But all I've done is I've added 20 grams of unspecified mass. So that's just because, as I said, in the payload section, you might want to fly, I don't know, an altimeter with a battery or something. And 20 grams, it's an arbitrary figure, but 20 grams is kind of gives you plenty of weight to play with up there. I've added a larger motor mount than the one in the example because I want this to be able to take 24 millimeter motors. So I've put in a tube that's 2.6 centimeters by outside diameter with a 2.4 millimeter inner diameter, and in there I've got currently an Estes D12-7 motor, which is, if you remember, is the 7 is one of the available delay timings for that motor, which I've set it to. Don't worry too much about that. We're actually going to, in the next video, I'm going to talk a little bit more about motor mounts because I'm going to do something, and it's highly probable that we're going to use one of the few things that we'll buy instead of salvage or make is the tube for the motor mount, but we're probably going to make the centering rings, and I've got some options again for I'll probably use my CNC cutter, but I've certainly got some options of cheap tools you can use to cut these centering rings by hand, which work really well. Yeah, fins again. Oh, actually, did I set the fin? Yep, I put the fins as 3 millimeter. I'll probably use some 3 millimeter ply. Oh, I've got those made out of cardboard. They shouldn't be cardboard. What I normally do for plywood is I actually use the birch setting because the weight is pretty similar. Yeah, so there we go. That's it in a nutshell. I've added a parachute. As I say, I added a Estes D12-17 motor, and I set the ejection delay charge to 7, simply again because I know that that's a motor that I actually have and is more commonly available. It presumably is available with a 5-second delay, but I don't have any of those. 5 seconds delay would actually be better off the simulation currently, but there we go. So I added that, and then didn't mean to do that, but on the flight simulation, This is the flight simulation. If we run the simulation, it had gone red then, incidentally, because I'd made a change. That's an interesting little tip. Say we make a change to something. Let's increase that body tube length to 41 centimeters from 40. If you go back to the flight simulation, it shows you that your flight simulation is out of date because something has changed about the design of the rocket, which is worth knowing. So then you can simply run it again and see the change, which is very useful actually if you're messing about changing perhaps like the profile of your fins or changing the weight distribution. You can see what effect it has on how high it goes and its speed and stuff. This is an interesting one here as well that we didn't talk about in the last video. Optimum delay. So this says the optimum delay for this motor is actually 4.18 seconds. So currently it has a 7-second delay, which is acceptable. It's not saying that we're deploying the parachute when we're travelling too fast downwards and risk ripping the rocket apart. But ideally, if we were buying motors and we saw some that were D12 5-second delays, that would be a better motor for this configuration. So there we go. We'll leave that video there for now. Hopefully that's got you started looking for tubes, measuring tubes, and perhaps designing around a tube that you've found. Next time we'll look at how I transfer, say, the nose cone into something that can be 3D printed, and how I use OpenRocket to output some stuff that I can feed into my CNC to cut fins and potentially centering rings and stuff. But also we'll explore other options that don't require you having all that snazzy kit. So that's it. Stay tuned, and yes, as somebody pointed out to me, I should say don't forget to hit like and subscribe. Ta for watching. Ta-ta.